Well, hello everyone. Hey, I kind of want to do something a little different today. Why I've got access to an actual computer, and I'm going to actually use a bit better mic system setup. I wanted to do a video on why 0.999 repeating is equal to 1. I've had actually a lot of people ask me this. I mean, I've done this for a couple years ago. This was a thing that was going around the internet, why 0.99 repeating is equal to 1. I know there's already been videos on it. I have a lot of comments on these particular videos in regards to this thing, so I'm pretty familiar with it. However, I have not done it in quite a while. So if there's anybody out there that's mathematically inclined, especially working with basic calculus, summations, geometric progressions, infinite convergence sequences and series and limits to sequences, all that kind of fun stuff, come on in, help me out here. I'm just going to take it pretty basic for the most part. I am going to use some of the things I have written before, and I'll explain them. If you're not interested in math, oh well, hey, you know what? I don't care. This is just for me, actually, more than anybody else, because when people ask me this, I'm just going to send them this video. But if you do like math and you do like going over these things, come on in, help me out. But I'm just going to start this off basically explaining what the actual issue is. 0.99 repeating is what's called a repeating decimal. And a lot of people look at that and they say, oh, well, it looks like it's less than 1. It looks like it's ongoing. It keeps on going. Well, the problem with that is that it may look like it's less than 1, but mathematically they're identical. They're equivalent classes. They're exactly the same thing equality-wise. And I'm going to actually have a couple of different proofs to do that, plus a couple of things that I've written to explain it. So I'm going to do screen share here, and I'm going to go into Word, my word processor here. So 1 second. Okay. I'm hoping this shows up. I know it's very hard to read some writing sometimes, but this should actually be something you should be able to see. I'm actually going to start off with the proofs first, and then I'm going to go into some of the other things that I've written about it. So what 0.99 repeating is this right here. This is called a series, okay? And what it's just basically saying is that you have 0.9 and you add it to 0.09 and 0.009, and yes, I'm saying O instead of 0, 0.009, and you just keep on going. Then eventually you're going to get this right here, okay? So the first proof is by proof by algebra, and this is a pretty simplistic one. This is the most common one people use, and this was actually one of the first proofs that Euler used to show that 9.99 repeating is equal to 10. And basically the way it works is this. All you do is you times each side by 10. So if you set x equal to 0.99 repeating, you multiply the left-hand side by 10 and the right-hand side by 10. You just move the decimal place over 1, just like you do in simple multiplication. Now, you got to remember that from here to here, there's an infinite number of 9s. That means you just keep going. You have an infinite amount. You do any finite process to it, you still have an infinite amount. So if you have an infinite number of 9s on this side of the decimal point, you remove 1 or you move it over, you shift it, you still have an infinite number of them. It doesn't change your quantity of them. So what happens is you times each side by 10, you end up with this. Now, if I want to subtract the initial value we have here for x equals 0.99 repeating, I'm going to actually make that over. Okay, so I'm going to subtract this from both sides. And on this side, I actually subtract the variable. So if I have 10x minus x, I'm left with 9x. On this side, I'm actually going to substitute what the variable stands for. So 0.99 repeating minus 0.99 repeating, this all goes away from here to here. So I'm left with 9. So I'm left with basically 9x equals 9. Divide each side by 9, you're left with x equals 1. So I started with 0.99 repeating, and I ended up with x equals 1. They have to be the same thing. They have to literally be mathematically the same thing. The second proof is proof by geometric progression. This is a little more complicated, but it's not really that hard to understand. What it's basically saying is that the same thing. You have your series, and if anybody's curious, by the way, there's a difference between a series and a sequence. This is a series. A sequence would be like this. That's a sequence. You can tell it's a little slightly different. Because on a sequence, you have 0.9, then you have 0.99 and 0.999. And that will come in probably handy later on, but that's a sequence. So Anyways, so basically we convert these to fractional form. So 0.9 is going to be equal to 9 over 10, obviously, in fractional form from decimal form. So we're just converting it from decimal to fractional. And then we can also say, what's the common factors we have involved here? The first initial one is 9 over 10, and the second one is just 9 over 10 multiplied by 1 divided by 10 raised to the first power. Next one is just 9 divided by 10 raised to 1 divided by 10 raised to the second power, and so on and so on. So this is what's called your common ratio. So what you do is your common ratio is set to 1 over 10. Your first term is obviously this right here in your series. Now, this is where it gets a little complicated, and I don't want to get too technical in it, but basically there's a formula out there. And when you have R, which is your right here, it would be R equals this. And I'm going to actually say A equals this. So when you have an absolute value of your common ratio is less than 1, or basically between the interval of -1 and 1, then you can actually use this formula here. Now, I couldn't figure out a way to get rid of the spelling and grammar checks. So what I'm going to actually do is I'm going to go over to a whiteboard here, and I'm actually going to write this little thing out so maybe we can see it better. Oops. Yeah, I just love pushing buttons. Okay, so I haven't used this too much yet, but I kind of messed around with it. So what we're going to do is we're going to make a little infinity symbol, okay? And then we're going to make a little summation symbol, and I will explain this, okay? And I'm going to say this is I, which means your index, and this is 1. After I draw it, I'll explain it. This is A, this is a little underscore, I, not minus. Then A divided by 1 minus R. I haven't really used these whiteboards much, so it's kind of cool. So what this saying is not as complicated as it looks. People get a lot turned off by math because they don't like the symbology, but this is really not that complicated. It's just saying a summation, and a summation is if you have, remember the old 1 divided by 2 plus, well, that's a crappy plus sign, 4 plus 1 over 8 plus 1 over 16 plus dot, dot, dot. That is actually going to, you add all these fractions together, you're going to get 1, okay? So what this is saying is the summation. So this is just saying that the summation of A, starting with your index of 1, is equal to this right here, okay, this formula, A divided by 1 minus R. And we can pop over back into what we have here. Where am I going here? Oh, my Word document, there we go. So what this is saying is this. We can use this formula here, and we can pop in the values we determined for up here. So if our common ratio is 1 over 10, we pop it in the R, and if our first term is 9 to 10, so we can pop it into here. So basically we have 9 divided by 10 divided by parentheses 1 minus parentheses 1 divided by 10 close parentheses. This is called parenthetical group. Now, just to make sure that this is correct, what I like to do is I like to go over to a thing called Wolfram Alpha, which I thought I had up, but I didn't. I really cannot type in the last couple of days. This is why we use Google and not Yahoo. Man, I'm telling you, I just cannot type. Okay, why don't we just type it like that? Oh, okay, so we're going to go Wolfram Alpha, which is a really great computational site. And we just type that little formula in and see what it comes up with. Oh, and look at that. Result is true. Okay, so we know this is actually a truism. So what we have is by geometrical progression that 0.99 indeed is equal to 1. Now, here's a little more technical stuff that I want to get into. Obviously, this is not going to be a very long video because I know people get bored very much with math. But again, this is for me, not you. I actually, on actually a couple of videos, one of them by Singing Banana, who's a mathematician, and Beihart, who's a recreational mathematician, who I think her videos are just absolutely amazing. I've posted these before. People have copied and pasted these, and that's fine. They've taken them and used this. I don't care. Everything I write is public domain, so it makes no difference to me. They don't give me credit, but that's fine. But what I challenge people that have a problem with 0.99 repeating is to answer these questions. And I think this kind of helps them understand that they have to be equal to each other. And yeah, this is a little bit more advanced in the geometric progression and the proof by algebra, but it's still not that complicated. So let me see if I got anybody in here yet. Nope. Okay. And nobody's watching either. I got 3 people watching. Yay, good people. 3 people that are going to like be better at math after the end of the day today. All right. So my first thing that I say is I am still screen sharing, right? I have nobody in here to tell me. So I'm just going to check on this real quick. Maybe I'm not screen sharing. Hopefully I'm screen sharing. If not, then you're just going to have to like guess that whatever I said is correct so far. So anyways, I say that all rational numbers by definition can be expressed in the form of a ratio of 2 integers, p over q, and then q, that little funny q symbol is actually meaning the set of all rational numbers, is equal to bracket p divided by q bar p comma q equals 1, and p, okay, basically what all this is saying is that p over q is a ratio of 2 integers, where the lowest common form is equal to 1. This is just saying over here that these are an element of z, which is our integers. Okay, this is this mathematical fancy talk for elements of z, integers, where q is not 0, where q is here as the quotient here is not a 0, because you don't want to have division by 0, because that's bad. The universe will blow up. So because all rational numbers are defined all repeating numbers are defined as rational, then you have to be able to express the 0.99 repeating in the form of p over q, which is 2 integers, 1 integer over another. What are those 2 integers? Well, obviously, if you don't think 0.99 repeating is equal to 1, you can't answer this question, because the 2 integers that you have that work for this are 1 over 1. So 1 over 1 equals 1, but 1 over 1 also equals 0.99 repeating. And that, I mean, obviously it works for any 2 integers are the same. I mean, p equals q, then obviously 9 over 9 is the same thing. 9 over 9 reduced form will be 1 over 1, which this is your reduced form thing here. And then you have 0.9 repeating. So again, if 0.99 repeating is a rational number, which by definition, all rational numbers are, all repeating numbers are rational, then you have to be able to answer this question if you think that this is 0.99 repeating is wrong. The second thing, and this one's a little bit more calculus involved, but it's still not that complicated. Basically, this is what's defined here. This is actually what repeating decimal is defined as in calculus. And all this is saying is that the limit of k as it approaches infinity in the summation of n divided by 10 raised to n, where n equals 1 to k, is by the definition of a limit of sequence. This right here, this n divided by 10 raised to the n, if you added these things together, if you did n equals 1, you did an iteration, you would end up at 0.9. If you put n equals 2, you end up at 0.99, 0.999. Again, this goes back to that series. Remember, actually, that sequence I talked about earlier when I said, a sequence is this. Oops. Okay, so that's what this comes out to be. So what's happening is, as you get more and more iterations, you get more and more closer to, you approach something, you get more closer to the number 1. Now people ask, well, you never get to 1. Well, that's not true, because we saw with the 1/2, 1/2, 1/2, 1/4, 1/8, 1/16, that does approach 1 and equals 1. Eventually converges, and it will eventually become that number. It's the same reason why people talk about Zeno's paradox. You fire an arrow to a wall, and you can say, well, at some point the arrow's halfway there, and then at some point it's halfway again, and then halfway again. Same thing with the 1/2, 1/4, 1/8. You're just taking, you're just doubling that 2 to 4 to 4 to 8. You're getting half and half and half. So eventually the arrow has to hit the wall. It has to, there's some way, reach the wall. This is what happens here. It reaches the 1. Think of 1 as the wall. So this is this mathematical fancy talk for the limit as it approaches will actually hit that number. And what I say here is that because the limit of k as it approaches infinity for this formula 9 divided by 10 raised to the n is equal to 1, both of these, both 0.99 repeating and 1, are equal to this right here. Both of these are correct. And if I remember correctly, if I cut and paste this and I go over to Wolfram Alpha, you see, somebody's got to come in here and let me know when I'm not screen sharing, because I seem to lose it every so often. So let's see here. I think if I type this in, actually just type that in and see what happens. Again, I haven't done this for a while in Wolfram Alpha. Oh, there we go. So if we just type this in here, look at what happens. It tells you that this formula, all this nasty mathematical stuff, is equal to 1. And as I said before, the definition of a repeating decimal is defined as the limit of the sequence of the number it approaches. That's called the convergence, or the limit of the sequence. So this right here is what 0.99 repeating actually is, mathematically speaking. So 0.99 repeating is equal to 1, because both 0.99 repeating and 1 both equal to this right here. That gets into the transitive property, which I'm going to address here in a few. So, oops. So let's go back to here. Please tell me I'm still screen sharing. Okay. So in other words, if both these are equal to the same thing, then you've got to explain to me why they're not equal. If 1 equals this and 0.99 equals that, they have to be the same number. A equals B, B equals C, therefore A equals C. Basic math. That doesn't apply to matrices, by the way. I'm just going to throw that out there. Anyways, the next one is a little even more complicated, and I'm really not going to get too technical on it, because when it deals with Cauchy sequences, I know very little. I know enough to get me by. A friend of mine whose name's Emperor Zelos, he's a mathematician friend of mine. He's a master at this stuff. So if you guys want to learn more about this, let me know. I'll get you in touch with him. But he reviewed this stuff, so I think it's pretty well correct. What it's saying is, a lot of people say, well, 1 minus 0.99 equals x. So I asked, what is x? And a lot of people say, well, it's this right here, 0.000.0001. Well, here's the problem with that. You know what? I'm going to close the door real quick. One sec. Sorry. Okay. Sorry. Okay. So obviously it has to be 0 if these two numbers are the same, correct? So one of the things that we do in math is infinitesimal small values are not allowed in R. And what this little fancy symbol is, it just means the set of all real numbers. Okay? But it's double strike. So that's just how we know it's a set for here. So, but due to the Archimedean property, so given no infinitesimals exist in R, please give the real value of x if x does not equal 0. What I'm saying here is that there's something called the Archimedean property, and that's just saying that in the reals, which is all the numbers you can think of, except for complex numbers, hyperreals, surreals, and other things, basically your regular numbers, your 0, 1, 2, 3, minus 4, 0.5, you know, basically, you know, what your elementary numbers, I guess you could, I don't know how else to explain it to somebody who doesn't know much about math, but your real numbers are negative infinity to positive infinity without invoking complex numbers, for the most part. And in that set, there's no such thing as an infinitesimal. The only infinitesimal allowed is 0. And this is because you construct a number, you have to what's called be able to take by a Cauchy sequence. And this is the same for epsilon greater than 0. There exists n such that m and n greater for a natural number. This right here is two sequences subtracted to each other. It's less than epsilon. Please give a sequence and show how it was converged upon this number. What this basically saying is fancy math talk is no two sequences, when you have them subtracted from each other, will converge upon that number. That number doesn't exist. Okay? There's no way you could construct this number using Cauchy or Dedekind cuts, or there's a couple other ways you can construct numbers. Again, not my area that I'm familiar with, but I know you cannot construct this number. It doesn't exist. It basically, this is exactly the same thing as saying 0, because it is literally saying I have an infinite number of zeros, and then after that, I have a number 1. Well, that's impossible. What decimal place it is. Every position in the decimal place has to have a unique position. So this has no unique position. It is literally after infinity, not making any sense. And then the last one is basically what's called the trichotomy property. And the trichotomy property is just basically saying that if you have two numbers, these are the relationships you can have. You can have x is less than y. You can have x equals y. You can have x is greater than y. But then you're saying if x does not equal y, there must exist x plus y divided by 2 between them, because the reals are dense. And basically what that means is that there's no holes in the real number line. For any two values I take, I can add them together and divide by 2. Any of them. Pick any two numbers you want. I can add them together and divide by 2. No matter how close to the number 1, I can pick any two numbers and I will still get something smaller. So I'm still approaching 1. The only way that this trichotomy property can hold here is that these two numbers have to be equal here. X and Y divided by 2 have to basically be the same thing. Basically, I'm saying 1 plus 0.99 divided by 2 is equal to 1. Same thing as saying 1 plus 1 divided by 2 is equal to 1. 0.99 repeating plus 0.99 repeating divided by 2 is equal to 1. So these are different ways that you can show people why 0.99 repeating is equal to 1. If they don't believe you at that point, then the reality is they're not using real mathematics. They're not understanding that in real mathematics, it's set up on certain axioms, certain properties, certain principles and theorems that they're just basically saying, you know what, I don't want to use any of it. And they can talk about hyperreals and surreals, but there's something called the transitive property that even in those types of mathematics, this still holds. There is no mathematics, unless you construct your own, which you can do, that this would ever not be the case where 0.99 repeating doesn't equal 1, unless, again, you construct your own version of it, or you're dealing with specific things in hyperreals where you can make them not equal, which is true. But we're talking about real analysis here. So anyways, I've given multiple different ways of 0.99 repeating was 1. Again, if people do not accept it, then they're just basically the equivalent of the flat earthers and the young earthers and everything else we always used to talk about, because they're denying reality. In this case, they're denying math. And as we know, math works. Why does 0.99 equal 1? It's because math works, bitches.